Welcome back. In this last segment, we're going to list a series of results dealing with the big O relationship, most of which will be important and useful to us in the future, even though we don't really have time to prove them here. For example, the second theorem in this lecture states that for any function f, f of n is big O of f of n. Before I give you a sketch of the proof here, let me mention that we're using the variable n on purpose to indicate that we're switching our focus to functions of integers now. So not only we're going to talk about integers, but we're only going to talk about positive integers. So from now on, n will be a positive integer, and say f of n will be a positive valued function. This makes sense to us since, again, n will represent the size of the input given to an algorithm, and f of n will represent the runtime or time complexity of an algorithm. So we can assume that all of these numbers will be integers and that they will be positive integers. Now, why is f of n, whatever f is, always big O of f of n? Well, the proof sketch is easy. Since f of n is always less than or equal to itself, this is essentially a trivial proof. Since this is always true, by definition, f of n is big O of f of n with the constant c, and k doesn't even matter. Now, the third theorem states that if f of n for all values of n greater than k is sandwiched between the value 0 and the value of g of n, which is another function, then it follows that f of n is big O of g of n. Again, the proof sketch is very short. This is essentially the definition of the big O relationship. If by assumption, when n is greater than k, f of n is less than or equal to g of n, and if all these values are positive, then the big O relationship stated here follows automatically. Now, theorem 4 states that if f of n is big O of g of n, and a is any positive real number, then a times f of n, first of all, that defines a function. It's a function that given n gives you a new value simply by applying f to n and then multiplying that number by a to give you the final value of this function. So not only when you multiply a by f of n, you get a new function, but that function, according to the theorem, is big O of g of n. So let's give a quick proof sketch of this theorem. So the assumption is that f of n is big O of g of n. And so this is the definition of this big O relationship. We use the constant c prime here instead of our usual c, that the name doesn't matter. So what can we infer from that? Well, what can we infer is that if this is true, then we can certainly multiply this number and that number by the same positive number a to keep the same inequality, and therefore it must follow that a times f of n, which is the function we're considering here, is less than or equal to this constant a times c prime times g of n. Simply rename the function a times c prime to c, and notice we have the definition here of big O relationship, namely a times f of n is big O of g of n, and that is the statement of the theorem. So what this theorem is saying is that if you know that f of n is big O of g of n, you can multiply that function by any positive real number. The resulting function is still big O of g of n. And the reason for that intuitively is because the multiplicative constant a does not make a difference in the big O relationship, since that constant gets folded into the constant that is already present in the definition of the big O relationship. Now, the next theorem states that if f of n is big O of g of n, and the absolute value of g of n is less than or equal to the absolute value of h of n for n greater than some k, then it must be the case that f of n is big O of h of n. So we have three functions here, f, g, and h. The assumption is that f of n is upper bounded by g of n, asymptotically. The second assumption is that g of n is less than or equal or is upper bounded by h of n. So the idea is the transitivity of the less than or equal relationship. If f of n is upper bounded by g of n is upper bounded by h of n, then f of n is upper bounded by h of n, up to a multiplicative factor, of course. And therefore, that's the definition of f of n being big O of h of n. So let's keep this result in mind in case we need that later. Now, before we state the next theorem, let's focus on a lemma that says for every n in a set of natural numbers, the numbers 1, 2, 3 and up, or even 0, 1, 2, 3, depending on how we define that set, it's always true that n is less than 2 to the power n. Now later on we're going to prove this inequality and this lemma using a proof by induction. But for now we can just intuitively understand why that is true. So if you start at 0, if n equals 0, it's clearly less than 2 power 0, which is 1. Even if you start at 1, 1 is clearly less than 2 power 1, which is 2. And then the idea after that is to realize that this function starts already bigger than this function. And this function, which is the linear function or the identity function, grows slower than this exponential function, 2 to the power n. So intuitively it makes sense that this function grows a lot faster and already starts larger than n for n equals 0 and 1. So this function will always be larger than this one. Again, this is all the intuition you need for now. We can prove this later. Now we can use this lemma to prove the following theorem that says the function f of n equals log n is big O of n. So here is a quick proof sketch. We know according to the lemma that n is strictly less than 2 to the power n. So what we can do now is we can take the logarithm base 2 of the left side of the inequality and then logarithm base 2 of the right side of the inequality. Because the logarithm is an increasing function, if the two inputs to the logarithm are in this relationship, then it must be the case that when you apply the logarithm to the left side, the result is still less than the logarithm on the right side. So we get this relationship here, and given the definition of the logarithm, this quantity here is nothing but the logarithm base 2 of 2 to the n, which is by definition equal to n, and therefore we just prove that log base 2 of n is strictly less than n. And therefore we proved this big O relationship with a constant c equal to 1, and I won't go into any more detail in this proof sketch. So what this is saying is the logarithm function, the logarithm of n grows no faster than n itself. And by the way, this argument also works if the base of the logarithm is different from 2. Now, the next theorem says that the function f of n equal to the sum of the first n positive integers, 1 plus 2 plus ... plus n, is big O of n squared. It's upper bounded asymptotically by n squared. Here is a quick proof sketch. 1 plus 2 plus ... plus n is less than or equal to this sum, which is n plus n plus n times. Now why is that? Well, clearly 1 is less than or equal to n. So it's 2. So it's 3 all the way up to n is clearly less than or equal to n. The reason for all of these facts is because n is the largest of the integers in this sum. So this being the sum of n plus n plus n times, it's equal to n squared. and therefore we establish that the sum of the first n positive integers doesn't grow any faster than big O of n squared. Let's conclude this segment with two additional easy results. Theorem 8 states that the function f of n equals n factorial is big O of n to the power n. This is an argument that we made earlier in this lecture. I will write it down as a proof sketch here and not say any more at this time. Finally, Theorem 8 directly follows from the previous theorem. It says the logarithm of n factorial as a function of n is big O of n log n. So here is a proof sketch. This statement follows from the previous theorem, and now all we have to do is to take the logarithm base 2 of both sides of this inequality, and again, because the logarithm is a strictly increasing function, we can apply it to both sides of the inequality and keep the inequality to yield this result. And now we just need to rewrite this logarithm. Remember that the logarithm of a product is the sum of the logarithms, and n to the power n is the product n times dot 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 times n times. Therefore, the logarithm of that product is the sum of the logarithms log n plus log n dot 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 plus log n times, in other words, n times log n. So in conclusion, the logarithm of n factorial is upper bounded by n log n, and that is the statement of the theorem. And this concludes our second lecture on the growth of functions.